Hey there, this is Professor Janacek, and I want to talk about surface integrals, but this time let's look at surface integrals of vector fields. To begin with, we'll let f be a vector field, or a vector-valued function defined on the functions f, g, and h. Now, if we're looking at a smooth-oriented curve, which we'll call S, it's defined by z is equal to g of xy. So notice z is in terms of x's and y's. Then our surface integral, S, by the way, notice that this is f dotted with n, the normal vector, and we're integrating with respect to the surface. Now we can actually write this and compute this using a double integral. And the integrand becomes negative f times the partial derivative of z with respect to x minus g times the partial derivative of z with respect to y plus h, and now we're integrating with respect to area. Now, of course, these functions can all be written in terms of x and y, and so we'll have to determine the order. Do we want to integrate with respect to x first and then y, or y and then x? Now, if S, still a smooth-oriented surface, is defined parametrically, notice it would look like R on the parameters u and v, and here x, y, and z are all written in terms of u's and v's. Now our surface integral becomes the double integral of f dotted with t sub u cross t sub v. Now, what is t sub u? That is the unit tangent vector in the direction of u, and t sub v is the unit tangent vector in the direction of v. So let's try an example here. Let's let f equal to the vector xyz. We want to find the flux across the slanted face of the tetrahedron z is equal to 10 minus 2x minus 5y in the first octant with the normal vector pointed upward. To begin with, I do have this tetrahedron graphed right here, so you can see that. You should be able to produce this graph on your own. Hopefully this one's not too bad. And we're looking for the flux. Now, if you recall, when we were looking at flux, it did have this form about it, although we originally looked at flux in terms of line integrals. Now we're just expanding that idea and looking at a surface integral. So we're looking at two parameters rather than one. Okay, so some things we need to kind of make note of. I'll be using this one because, oh wait, actually is that? Yeah, that's probably going to be the easier one to work with, because we have z written out for us. All right, so let's see. First off, just need to notice that f is equal to just x, g is equal to just y, and z is equal to just h. Of course, remember f, g, and h could be in terms of any of those three variables. Hold on, I wrote that backwards. Let's see, that's h is equal to z. But z we also know is 10 minus 2x minus 5y, so h is 10 minus 2x minus 5y. All right, also we're going to need the partial derivatives of, I'm going to notice anyone need the partials of z. So looking at z, here's z, the partial with respect to x is negative 2, and the partial with respect to y is negative 5. Also want to make note that the normal vector, in case we need this, is the vector, it's the opposite of the partial of z with respect to x. For the first component, the second component is the opposite of the partial of z with respect to y, and the third component is simply 1. So in this situation, we have 2, 5, 1 as our normal vector. So if you wanted to go through and compute this using the surface integral, we could, but I think we're going to go ahead and write this in terms of a double integral. So our surface integral, f dotted with n ds, we're going to write as the double integral over our region R of negative f times the partial of z with respect to x minus g times the partial of z with respect to y plus h dA. Okay, I do need to figure out the values. Remember, dA in this situation is going to be dx dy or dy dx. So let's talk about those values. So I want to find out that area. So this area that we're integrating with respect to, that area is the area of the base of this, the floor of this tetrahedron. So for z equal to 0, which would give us the floor, we have that 10 minus 2x minus 5y is equal to 0. And we could solve, either for either one of those. I'm going to go ahead and solve for x. Solving for x gives us, watch those negatives, you end up with 10 minus 5y divided by 2. All right, so that tells us that x is going from 0 up to this value in terms of y, and of course we can see that the y value will go from 0 to 2. So I think that tells me the order in which I want to integrate. I'm going to integrate with respect to x first because it's defined on terms of y, and then I'll integrate with respect to y. So now we can set up this double integral. Since I'm integrating with respect to y secondly, that's the one that's going to be on the outside, so I'll integrate from 0 to 2, and then from 0 to 10 minus 5y over 2. And then our integrand is the opposite of f, which is negative x, times the partial of z with respect to x, that's negative 2, minus, minus g, which is just y, times the partial of z with respect to y, which is negative 5, plus h, which is 10 minus 2x minus 5y. And we are integrating with respect to x and then with respect to y. But before we do that integration, let's clean this up just a bit. Let's see, what does that give us? It gives us 2x plus 5y plus 10 minus 2x minus 5y dx dy, and look at that, we can simplify that even more. We have the double integral of just 10 dx dy. Whoa, okay, can definitely do that one. So integrating with respect to x first, we get 10x, evaluated from 0 to 10 minus 5y over 2. And don't forget that differential for y. Evaluating that, that's pretty simple. We still have the integral with respect to y, but now we have 10 times 10 minus 5y over 2 minus 0, but of course we don't need to write that. So let's see, simplifying this a bit might help. That gives us, what, 50 minus 25y for that integrand. Now we're going to integrate with respect to y, so we get 50y minus 25 over 2y squared, evaluated from 0 to 2. See, evaluating at 0, we have 100. Minus, reduce a 2, that gives us 50. And then minus 0, of course, which simplifies to just 50. And there we go. Not too bad. Enjoy.